picking up where we left off, we had just calculated that our 33 grams of ibuprofen was in fact 0.16 moles of ibuprofen. And next, they want to know how many molecules of ibuprofen are there. So how many of the molecules C13H18O2 are in 0.16 moles of it? Well, fortunately, we can use Avogadro's number to convert from moles to number of particles. So we're going to take our 0.16 moles, and we're going to take it times Avogadro's number, because we know that there are 6.022 times 10 to the 23rd molecules in 1 mole. So our moles cancel, and we are left with our molecules, which, if you do the math, comes out to about 9.6 times 10 to the 22nd molecules of ibuprofen, C13H18O2. All right. The final question that they have is, what is the total mass in grams of carbon in 33 grams of ibuprofen? So we have to go back to our moles number that we had at the beginning. We have 16 moles, but it's important to note that this is moles of ibuprofen. I'm just going to write moles of I for short. Then we need to figure out how much of that is going to be moles of carbon. So if we look up here at our formula, we see there are 13 carbon atoms in 1 molecule of C13H18O2, which means we can use the conversion factor that for every 1 mole of ibuprofen that we have, we're going to have 13 moles of carbon. And so if we worked this out, it would give us how many moles of carbon, because the moles of ibuprofen would cancel and we'd be left with moles of carbon. But they don't want just moles of carbon. They want grams of carbon. So then we need to take this one step further and convert from moles of carbon into grams of carbon. And to do that, we need carbon's molar mass. So we can look back at the periodic table and see that carbon has a molar mass of 12.01 grams of carbon for every 1 mole of carbon. And so then moles of carbon cancel, and we're left with grams of carbon. And if you work the math out on this, you're just taking 0.16 times 13 times 12.01, and you will come out with approximately 25 grams of carbon. So a large portion of the grams in the bottle are made of carbon, which, if you look at it at the formula and you know the molar masses of the objects in question, that makes sense, right? There's 13 carbon atoms compared to oxygen atoms. So even though oxygen atoms weigh a little bit more, there's far fewer of them. And yes, there may be 18 hydrogen atoms, but hydrogen atoms do not have a lot of mass. So it makes sense that even though there's a lot of them, they don't make up a large portion of the mass in the bottle. All right. Moving forward, we're now going to learn a new skill called percentage composition. And you'll pardon my baby screaming in the background. Sometimes it's nice to know what percentage of the mass of a compound is made up of one specific element. For example, if you want to use KClO3 as a source of oxygen, it would be nice to know what percentage of that mass that you're getting is going to be oxygen. So you know how much total mass of that substance you're going to need to get the oxygen that you require. There are two ways to solve for the percentage of an element in a compound. The first is to take the mass of the element in a sample of a compound, so weigh the mass of the element, and divide it by the mass of the sample of a compound. This would be the same as if you were trying to find out what percentage of your trail mix was M&Ms by mass, right? You'd weigh all of the trail mix together, and then you'd weigh just the M&Ms, and then you'd take the mass of the M&Ms divided by the sample, by the mass of the trail mix, and you'd multiply it by 100, and you would get the percentage of your trail mix that was made up of M&Ms. This method is nice, but it has a flaw for some chemistry, which is that for this method, you have to be able to take a scale and measure the mass of the element in the compound. And that's not always practical, right? I can't just take KClO3 and just sort out the oxygen atoms and weigh them. So we have a different, more mathematical method that we can use, and that is to take the mass of the element in 1 mole of a compound, and then divide it by the molar mass of the compound and multiply it by 100. Okay. So, for example, if I wanted to do this with barium fluoride, I would need to first solve for the molar mass of my compound. So starting with barium, I would have, 137.3 grams of barium. Okay. And then there are, the mass of fluorine, I have to look up, is about 19 grams. But I have to multiply that times 2, obviously. So that looks more like a plus sign than a multiplication, doesn't it? Okay. Times 2 comes out to 32-ish. More like 32.98 is what we're going to use. And that would be grams of fluorine. Okay. So our total molar mass, when we add those two up, comes out to 175.3 grams per mole for our barium fluoride compound. So now if we're going to use this formula from up above, we're going to take mass of the element in 1 mole of the compound. So for barium, that would be 137.3 grams. And then we're going to divide it by the molar mass of the compound that we just solved for. So we do 175.3 grams. And then we're going to multiply that times 100. And if you do that math, you should come out with about 78.32% barium. And then you can repeat the process again using the mass that we solved for of how many grams of fluorine, which I must have made a mistake calculating up here because it should come out at 37.98 grams, and then we're going to divide that by the molar mass. And multiply it by 100. And come out to about 21.66% fluorine. So while there is more fluorine in this compound, the mass of fluorine is significantly less, which means it makes up less percentage of the mass. And then you can look at your totals and you want to come out pretty close to 100. Now, because of rounding things, it's not always going to come out to exactly 100, but you want to be in that ballpark. We would be at 99-ish%. So we'd be very close. Okay. All right, I'm going to erase what's here on the screen. Oh boy, I'm not doing a great job of erasing. This is a new tool, guys. Sorry if it's a little... Okay. This method is more practical because it lets you use known values to do your calculations, so you don't actually have to weigh anything. All right, so now that you've seen a practice problem, go ahead and pause the video here and try to find the percent compositions of the following compounds. And then when you're done, unpause and watch me do them. Okay? All right. So we got to start by calculating molar mass. So we know carbon is 12.01, and we're going to have to take that times 3. And then hydrogen is 1.01, and we're going to have to take that times 8. So if we run those calculations, we will, I'm certain, come up with numbers. So for this one, we're going to get 36.03. And then obviously we'll come up with 8.08. And then when we sum those, we'll come up with 44.11 grams. So that is our molar mass, grams per mole, of the whole compound. So now we're going to take grams of each substance in the compound divided by the molar mass times 100. So for carbon, that is 36.03 divided by 44.11 times 100. Let me do the math on my calculator real quick. Comes out to about 81.68%. And then for hydrogen, if we do it, we're going to put 8.08 over 44.11 times 100 comes out to about 18.31%. And so then if we sum those up, we would find that we're at like 99.9%. So we must have done this correctly. All right, let's do the next one. So this one has slightly more in it, but we're going to follow the same procedure. So we'll just start out with sodium, which has a mass of 22.99. And we don't need to take that times anything. So we can just carry it over here. And then hydrogen, again, 1.01. And we don't need to do anything to it because there's only one of those as well. And then sulfur, which has a weight of 32.06. Again, only one sulfur atom, don't need to do anything to it. And then lastly is oxygen, which we know to have a molar mass of 16, but this time we do have to multiply that by 4 because there are 4 of them here. Okay. And when we do that, we get 64. 0.00. So then when we sum all of these up, we're going to come out with about 120.06 grams per mole, which is the molar mass for NaHSO4. And now we can just repeat the process from above, where we take each element. So Na, sodium, we would do 22.99 divided by our 120.06 times 100 to get our percentage for that one. Comes out to 19.15-ish%. And then we can do the same thing for hydrogen. This one, as I'm sure you've already guessed, is going to be a very small percentage because there's one hydrogen atom which has a mass of approximately 1 U. So this isn't going to make up a large portion of our mass here. And then take it times 100. Yes, so if we get this, we're actually going to have a point, this is going to be a 0.84% hydrogen. So not much. Then we'll do sulfur, which we said was 32.06. So once you've figured out what you're doing here, this just becomes a repetitive process. And it's much more difficult to write on here than it is on my iPad. So I'm a little slow, but bear with me. And we come out with 26.70%. And then the last one would, of course, be oxygen. So for that one, we do 64, because remember, it's not the molar mass of the compound, but it's the mass of that element in 1 mole of it, which we calculated over here. And we're going to divide it by 120. And then multiply it by 100. And this is approximately 53.30% oxygen. So then if we total up our percentages to make sure we're in the ballpark, we end up with, well, let's just see, 19 plus 0.8 plus 26 plus 53. Gets us in the 98.8% range, and I didn't even use the decimal places, so we would be even closer. So we are very close to 100%, which means we have likely done our math correct here. All right. Your homework is the review questions from the end of this chapter. There are 5 of them. Some of them are going to be very similar to the problems that we did in the notes together, and some of them are going to be a little more application. So if you get stuck, just know that I will be back in class tomorrow, and we can go over them then, and we can really hammer in on the parts that don't make sense. All right.